Ready? Hi.
Here, I'm going to introduce you. All right. My clock says it's time to start. So when I created the slides for today, it kind of bugged me that I had that blank line there. Kind of bugged me that I had the blank screen. It kind of bugged me that I had the blank line in the slides. And I got to class, and magically, there is an issue that's going to fill that blank line. So to give you that insight is Shivani.
Thank you. Hi, guys. So, Hack Illinois is looking for volunteers for the spring. So Hack Illinois is coming up on February 24th, which is a Friday. It's going to be a weekend-long event here in Siebel, ECB. And if you could help out, that would be awesome. We have a sign-up form on...
Hold on just a minute.
Ooh, sorry.
Hack, is it go dot?
Go dot, yeah. So go.hackillinois.org/volunteers. Thank you. So we would really appreciate it if you could sign. We have lots of time slots available. If you could help out, that would be awesome. We also have a Facebook event that's Hack Illinois, no spaces, and then a space 2017. So you can check that out. We have the form linked on there too. And yeah, so that would be awesome. Thank you.
Okay. Thank you so much. It's really fun. It's like a weekend-long slumber party. Raise your hand if you've participated in Hack Illinois before. I mean, as in any capacity. Really? This is like a life changer. If you haven't participated in Hack Illinois in the last couple years, figure out a way to do so. It's a blast. All right, and there's cool stuff here. I should probably erase that. I don't know. Okay. I also wanted to spend a little bit of time talking about the exam. And in order to do that, I want to do it in the context of MP2. Okay? Now, here's what I want you to do. I want all of you, even you guys who are talking, I want all of you to think about the amount of time you spent on MP2 or you anticipate spending, if you haven't quite finished it yet, on MP2. And I'm going to ask, okay, how much time did you spend on MP2?
8 hours.
8 hours, and you're lucky. Yeah, I think that's an underestimate of how long it might take. Okay, how long did you take on MP2?
Several nights.
Several nights, okay. Not even a number for sure, okay? And yet, how much of your grade is it worth? How much of your grade is MP2 worth?
2%.
2%. Almost nothing. Okay? Now, the way we give you credit for your hard work on these MPs is to test you over the material that you have learned. So in a sense, we give you 2 percentage points for having gone through the work and the creative process of making it. And we give you about 2 more percentage points for showing us that you truly learned it on these little programming exams. So at least half, or about half, of the programming exam that we're going to ask you to do is going to be closely related to the understanding of writing code that you gained from MP2, guaranteed. What that means is that there's going to be an emphasis on dynamic memory allocation and deallocation and cleanup. So building your mess and then cleaning it up in the same sense that you had to do for MP2. Okay? I've just told you what's on half the test. The other half of the test is little examples from class and lab. So smaller pieces of code probably that illustrate that you understood what was going on here, and that at the worst case, all you would need is a compiler to untangle your thoughts. Okay? Any questions about that? Is that good? Okay. All right. So let's get working today. We're going to do something new and exciting, but it follows very directly on something that we did before. So last time we were talking about inheritance, and especially we were looking at what we call polymorphic behavior. That is, we were looking at ways of making a single function, in this case the speak function, behave differently depending on the type of object for which it was called. Okay, so for example, in that case, this speak function, the speak function that applied to farm 1 or farm 0, which was a dog, was a completely different function than the one that applied to farm 1, which was a completely different function than the one that applied for farm 2. This idea that objects of different types can employ functions of the same name and parameterization is the very essence of what we call polymorphism. Okay? All right, so now, using inheritance, you can do this on the fly. You can do this at runtime. The implication there is that it can be conditional. You can gather user input to decide what kind of noise you'd like out of your farm. You can do it based on the time of day. If it's early in the morning, maybe it's the roosters that speak. You can use runtime state to determine what those, which of the functions should be deployed, okay? Now that comes at a performance cost because all of those possibilities have to be available, which means you can't, you can't not implement speak from all the different possibilities because there would be a danger that it wasn't there, okay? So it can be done. It comes at a bit of a cost. From a design perspective, you probably shouldn't worry about that cost, but just being aware that there's a slight issue there is probably reasonable. And the thing that makes it expensive is because the determination of what that function should do comes at runtime. Now, in contrast, if you know ahead of time exactly which versions of functions should be called in which contexts, if you know ahead of time, that is, if you know at compile time, then you can use a different construct for polymorphism. The construct that we're going to use is called the template, the C++ template. And we're going to spend the rest of today talking about how templates work. The key thing to kind of have in the back of your mind is that we are prescribing compile time behavior. We're prescribing how the code is compiled, not how it executes. Okay, so let's start this off. I have an example. I want you to take a look at the example, and I want you to make 2 observations, and I want you to actually write them down, okay? I want you to make 2 observations, and I'll give you the heads up that both of these observations, if you're going to ascribe an emoticon, they get a sad face. Okay? Take a look at this code, see what it does, and see what bugs us about it. Anybody got anything to say to me yet? Yeah? Oh, it's the same code written twice. Imagine if this were a big chunk of code and I paid a contractor $1 million to do that one and $1 million to do that one. That feels like a waste, right? So this is repeated code. Okay, this is wasteful. Moreover, it's irresponsible because if we came up with some fancy way, some newfangled fancy way of swapping two variables, we would have to know all the different places where we'd have to update the code, right? If I come up with a new algorithm for swapping variables, feels a little bit silly to say even, then I would have to go back and change not just that function, but also that function, and think about the implication. It means, number one, I would probably miss one, right? Oh, shoot, I got integers and I got characters and I forgot to switch shoes, you know? Furthermore, the more code I have to update, the more likely I am to induce new bugs. So I really don't like having to modify lots of different pieces of code, okay? There's another frowny face about this. So that has both, it has maintenance issues. There's another frowny face about this. Yes? What? Oh. Raise your hand if you caught that one. Okay. Yeah, so the other frowny face thing is that both of these functions, not just one of them, but both of them actually don't do anything that we can see. I mean, they do. They swap local variables because it's fun or something. I don't know. But there is actually no evidence from these couts that those variables were ever swapped in any scope. Okay? So they don't work. Neither function actually swaps A and B, despite their name, despite the names of those functions, right? Okay, so how do I fix that? Yeah? Either one of them. How do I fix that this problem? How do I fix the second frowny face? Yeah? Yeah, I'm going to pass by reference. I take option 2, okay? So the suggestion was we could pass by pointer or pass by reference. We could pass by pointer, but that means then we need to make sure they're not null and take care of our pointers because they're fragile. We're going to prefer to pass by reference here, okay? All right. Like this. Oh, what the heck am I doing? I might as well just go on to this example. Okay? Okay. So what we have done and what we can do is we give ourselves the ability to pass type information as if it's a parameter. Okay? The keyword that I use to do this is keyword template as a preface for the function signature. Okay, so template says the following function definition is going to have a type that needs to be instantiated. Okay? All right, and now, furthermore, this keyword class is used to designate the fact that it is type information that we're instantiating. There are alternatives here. It's equivalent to the keyword type name. Okay, so sometimes you'll see class, sometimes you'll see type name. I chose class here because class is a shorter word, and I'm always concerned about screen real estate. Okay, and that was really the only reason. Okay, so now let's think about what's going on here. It's as if those angle brackets surround a parameter list where the parameters are types. So I can send a type in. It's referred to inside the function as this token T, and everywhere you see a T, it is as if that type is used. So, for example, in usage, I'm going to answer you in just a second, okay? In usage, I'm going to say swap us, because that's still the name of the function. I'm still going to pass in a couple parameters, just like I did before, but I'm going to add a type parameter. That's an angle bracket, and these are ints. Okay? Just like that. I'm going to pass more information in. Similarly, in the second example, I'm going to call swap us again, but this time I'm going to pass in char as the type name. All right? And now, here's what happens. Here's what happens upon compilation. The compiler looks through this code and says, okay, I need swap us with an integer. It takes that code and it writes essentially this, except it's called swap us instead. Okay? The key is that it uses ints. It makes that machine code. It uses that version of swap us. Okay? Or it creates that version of swap us. Then it comes along and it sees this one and goes, oh, look, I need another swap us. It goes out and it creates the machine code for swap us instantiated with char. So in the end, you get exactly the ones that you use. Exactly the ones, the versions of swap us that are made are the ones that are used in main. Okay, and then there they are. All right, any question about that? Yes? Yep. Really good. Okay, so the question is, does this work for user-defined types? And the answer is sure. And to determine whether or not you need to make that object robust in the same sense that we did when we were talking about the big three, etc., you use all the same criteria. So if your object needs, if your user-defined type needs a copy constructor, you better make one, and this will use it. The way to check whether or not your user-defined type will work in this templatized function is simply to, let's say our user-defined type is a sphere. Ugh. Okay, let's say our user-defined type is a sphere. All I have to do to check to see if this makes sense is put a sphere for every t. So temp is a sphere, x and y are spheres. I can swap them back and forth because spheres have operator equals, right? Spheres have assignment operators. So that will be fine. Okay? Things get a little bit more complex if you're using this for pointer types, but you can do so. You are just responsible for making sure that everything the system is going to need is provided. And we'll talk about that a little bit more as we go through, as we get to more interesting examples. Yeah? Very good question. So the question is, just like in normal parameters, like, look, I could put as many value parameters as I want to here. Could I use more than one type? And the answer is yes, and I'll show you the syntax for that in a later example. Okay? All right. Oh, one more thing. The use of that capital letter T there, that is capitalized by convention. So it's very typical for templatized types to employ capitalized strings. And I don't know why, but they're always usually short, right? Like T, U, V, whatever, or W. All right. Any questions about it? Yeah? It's the same as if, so the question is, what's the scope of the declaration of that function or of the template? It only modifies that function. Okay, so template there modifies only that function. Okay? All right. But I think I know what's bugging him. He's like, well, is that really all we can do with these things? And the answer is no. In fact, we can make templatized classes as well. So imagine that your private member for a class, maybe like a scene class or something, contains a dynamic array, say, or an array. You can use that class to hold any kind of thing via a template. So for example, I could specify that this class holds animals or ints or whatever, and I can make this array contain those things. Okay, and I'll show you the syntax for that in a minute. We call such things container classes, and I assert that you are already familiar with them because you have heard somebody say the phrase standard template library. That the standard library for C++ is actually a standard template library. Okay, so you're allowed to pass type information to these things. Let's see, we haven't used it a lot in this class yet, but we will. Oh, I forgot to say something on the previous slide. Can I do it? Do you care? I'm going to go backwards for just a sec. Okay, it's here. If you forgot to write this here, if you forgot to pass in the parameter explicitly, the system's pretty darn good at inferring it for you. So you're very unlikely to actually get a compiler error by not doing this. If it can't figure it out, if it can't figure out what this is supposed to be from these things, if there's any ambiguity at all, then the compiler will say, yo, I do need that type information, okay? So I just wanted to add that in here. Okay, let's see. Now this doesn't just hold for classes where the private data is a dynamic, as an array. It holds independent of the way that data is stored. So we don't know much about what this is yet. Monday's the day we're going to start actually talking about data structures. But suffice to say, this is little tiny blocks of memory all kind of linked together, a list of little blocks of memory all linked together. And we don't care very much about what kind of thing goes inside of it. And so we allow the type information to be templatized. Okay? We could put spaceships in there if we wanted to. Okay? Anything we want. Okay, and then similarly, in another form of foreshadowing, okay, here's a structure. We're eventually going to talk about things that look like that. And we're not going to think very hard about the kinds of things we put in it. We're going to be much, much, much more concerned about the structure itself. Okay, so what's the syntax of how this works? Well, I've simplified it down as far as I possibly could to make a class an easy pair. Okay, so take a look at an easy pair for just a second. It won't surprise you that an easy pair has that many data elements associated with it, right? What type are they? We don't know. It's parameterized. We can make them be a pair of anything we want. A pair of integers, a pair of shoes, I don't care. The syntax for doing that is to preface the class definition line with exactly the same syntax that we saw for functions. Okay? Yeah? Things work. I'm gonna pull that out of everybody at the same time. You're asking exactly the right question. Okay? And I think we're gonna address it in the narrative. You let me know at the end if we haven't addressed it. Okay? Right. So it feels crazy. It feels crazy to be able to just put any old type of thing that we want in a box here, right? Like it's putting a pair of shoes in a box, kind of here. We don't know anything else about the functionality. But what this class basically promises to do is just hold those things for you. All right. I want you to tell me, what is this line? What is that? A constructor, very good. Okay, and notice again, we've used that parameterized type to specify what those constructor parameters need to be. Let's, okay, good. I don't know what order I'm going to do this. All right, what is this one? It's a function. What does it return? Something of type T. Okay, what do you think it does? If I give you a function called GetMax of two things, what do you think it should do? Return the bigger of them, right? That's kind of what you hope. Okay, all right, let's go with that for now. Now I want to show you how to use this. There's nothing here that will surprise you yet. I'm going to declare an easy pair of integers called 2nums, okay? And I'm going to invoke that constructor by saying 175 there. Any question about it? Okay, and then now 2nums is an easy pair of integers, and so I can call its member function, GetMax. Let's take a look at GetMax. There are a lot of things to talk about here. First, the heck. What's going on there? Ah! Yeah? Yeah, this is a ternary operator. It reflects laziness on your teacher's part. Okay? So it's just an if statement. It's a very simplified if statement. Here's how it works, in case you haven't seen it before. Here's how it works. There's a Boolean expression here. If that Boolean expression is true, that value is returned. Otherwise, this value is returned. What does the type of this have to be? What does the type have to be? The same as A, yeah, that's true. What else? The same as GetMax, which is the parameterized type. Okay, so that value has to be of type that can be assigned to GetMax. Okay, any question about that? So this is just shorthand for if A is greater than B, return A, else return B. Okay, yeah? Well, you tell me, what does it return if they're equal? B, because that's the else, right? If A is greater than B, that's strictly greater. Okay. Okay, let's see. Now, I have what I think is an interesting question here. What happens if instead of int, I say animal? Dog, cat. Yeah? Yeah, look what GetMax does. It says if A is greater than B, if dog is greater than cat, raise your hand if you think dog is greater than cat. Raise your hand if you think cat is greater than dog. This is not a clear-cut answer, right? There are dog people, there are cat people, and we would go to war if we had a deep conversation about it, right? So the observation which is key here is that whatever type of thing we pass in, the parameterized type T must have a definition for operator greater than in order for this to work. What I'm hoping is that This addresses the question posed early in the hour where he said, but wait a minute, what if the type of thing you're putting in there doesn't work? This is, well, it's only going to work if all of the elements that you try to execute on it are actually defined. Okay, so in this case, would you expect this to work for animals? Straight out of the box? Hard to justify. Could you define a greater than for animals? Maybe. Maybe by size, maybe by weight, maybe by name of the, C is less, I don't know. Maybe you could. But you would have to explicitly do so in order for this code to work. Now, what do I mean by to work? To compile or to run? To compile or to run? Compile, that's right. In this case, using templates, the code will not even compile if it can't find all the pieces it needs, okay? Which is good. That's good news. We like it. We have a shorthand for the constraint placed on types that demand that this operator greater than is defined. We call them comparable types. So I can rewrite this same thing to say T must be a comparable type. And really that means all of the comparison operators are defined. And they can either be defined by default, like for integers, or they have to be explicitly defined for user-defined types. Yes? Yeah? The compiler is going to tell you. The compiler barfs. It says, sorry, no definition for greater than operator. In the comments. In the comments. Yep. I mean, if you go look at the documentation for the standard template library, you'll see this stuff all over the place. They'll prescribe you either have to give it a comparable type or you have to give it a comparison operator, right? If you want to overload the comparison operators, you must provide them with the class. Yeah? Then it would work fine. So if you only defined greater than and we only ever ask it to use greater than, we're golden. Okay? Is that great practice? It's kind of a bad idea. Usually when you create any kind of comparison, you sort of assure that things are comparable. Okay. Any other questions about this? Yeah? Yeah. If you don't call the function GetMax, no problem, no big deal, because the compiler won't go looking for it. Okay? Yes? No, I think you need to explicitly define both of them. Okay? So if you're making a user-defined type and you want it to be comparable, you have to do a ton of busy work, basically. Okay? All right, anything else? Yeah? Oh, brother. Okay. So the question is, can you inherit a templatized class? So, MP4, I think it was. MP4. We went around and around and around and around with the way that we would put templates together with inheritance. And what we decided in the end was that we were making it too complex. If it was too complex to document well, we were trying to do something that we shouldn't have been trying to do. Now, that is not to say that you can't have great discussions around the interplay between templates and inheritance, but you better have really good reasons for doing so. And you actually do know all the information that you need to do this. So, to answer your question, I'm interpreting your question to be, can a template class be a base class? Yeah? And the answer is, if the thing you're passing in, if the way that you use it in your code creates something that's a valid base class, then yes, absolutely. Okay? And those rules are kind of coherent. They make sense if you think about how you're going to instantiate that template class all the way along. Okay? Yeah? I'm gonna get there. I have a slide for that. So we're talking a lot about compilation, and so we should spend some time talking about compilation, and we'll do that in just a second. But first, Mark, you have a quick one? Okay. If you're asking questions that are more complex, especially about this interplay between templates and inheritance, I'm going to put them off because those end up being whiteboard discussions, and I have no whiteboard. I don't think they want me writing on this screen. So I'm going to put that off, okay? Oh, I know. Let's do this really quickly. So I have a few little challenges for you that are kind of unanswered questions that I think you already can infer the answers to. In particular, I want to know what would the function signature be for the copy constructor of the easy pair class if we needed one. If we needed a copy constructor, what would the function signature in the .cpp file look like? And I'm wondering if anybody would be willing to write their answer on my tablet. Yeah? No? No way? Okay, you pick somebody to write their answer on my tablet. Okay, you can point to somebody. You can choose somebody. All right, you're up, Mark. Okay. Now, what I want you to do is be sure to make a mistake. Okay? Be sure to make some error, because otherwise I wouldn't have something to talk about. So, all the rest of you should put your noses down and think about what the function signature for the copy constructor looks like for this class. There's a big hint in green if you want to use it. Okay. Thanks, Mark. I think I asked you to make a mistake. Did he make a mistake? Yeah, okay. We'll find it. I don't know if he made a mistake yet. All right. So we also want to, we don't know what T is unless we make the template statement. So we're always going to add on template class T as part of this whole thing, much as we did right here. Okay? Much as we did in the green there. We're going to preface the whole thing with template class T. And now now we can use T. Okay, now we can use T. Easy pair has a little e. Got it. I got it. Okay. Phooey. Sorry. Easy pair T. Good. And what you notice is the name of the constructor is still just easy pair. just as it is up here, okay? So in this context, we do not specify the templatized type in the function name. A little bit different than we saw before. Is it? Yeah. Okay, and then finally, we've got the parameter. In contrast to what I just said, that we don't give the type information in the function name, we do give the type information here. So instead of easy pair, because we're talking about types, is the way I remind myself, we do specify the templatized type there, because it's a type name, not a function name. Okay? How are you doing? Okay. And now that's complete. Okay, how do you declare a dynamic array of my pairs of integers? Do you want my tablet? Yeah. Okay, you name somebody. You point to somebody who you're going to give my tablet to. There's like 200 people in this room. Yeah, okay. You want my tablet? Okay. So answer question 2. You guys should all answer question 2. Be sure to feel free. Oh, you need my pen. Feel free to make as many mistakes as you like. Okay, how do you declare a dynamic array of my pairs of integers? Dynamic array of pairs of integers. Oh, it should be easy pair. I'm sorry, that should be easy pair instead of my pair. Sorry. The operative word is declare. If you want to also allocate the memory or define it, that's challenge number 3. So the first one is not going to have an assignment statement in. Oh, sorry, I wasn't watching. Yes, the first one is just a declaration. Of, it's the hardest thing in the world, isn't it? Oh, I know what I did to make it hard. Here, I see what's hard. Let me see. I can do it. It's fine. Okay, thank you. Sorry about that. I didn't say what to name it. That's part of it. So, how do you declare a dynamic array of my pairs of integers called fun? Because we need some fun right now. Okay? All right. Yeah, and this should be easy pair. Okay? All right. So, I don't have any idea how to start this, except that I know that to declare a dynamic array, I'm going to need an asterisk, right? I know that this thing is going to need to be a pointer. I also know that its name is fun. Now the mystery is, what does the type look like, right? If it were a dynamic array of integers, we would put int right there. It isn't a dynamic array of integers. It's a dynamic array of pairs of integers. Easy pairs of integers. Okay? So just like we've seen before, the name goes here, the asterisk means it's a dynamic array, and all of this is the type information. It's not a dynamic array of pairs of animals. It's not a dynamic array of pairs of spaceships. It's a dynamic array of pairs of integers. Okay? Does that make sense? All right, now let's give it value. We are going to let fun equal, what gives us value, allocates the memory? New, good. New, what type of thing do we want? An easy pair of ints, and how many of them do we want? 8, good. Okay, so recognize that together, these two things is what determines the type. Easy pair of integers, easy pair of whatevers. Yeah? Oh, how does it initialize each element? Yeah, there's no, it'll call easy pairs default constructor for you, just like any old other array would do. Okay, I think. Yeah, we didn't declare one. That's okay. So the behavior will be the same. It'll look here and see whether or not it can do it. So actually, this might give you a compiler error. Yeah, okay, good catch. Okay, yeah? So the behavior is the same. It's just as if we always define the whole thing as an easy pair of integers. Yeah? So to get the memory for the dynamic array, you need to say new. Yes. Okay? All right, there's one more thing we need to talk about before we go. It's the last thing on Friday. Oh, no, 2 more things. Okay, the question is, what happens when we invoke this code? And what I want to point out is that I'm showing you here the syntax for 2 parameterized types. Okay? We're not going to think about it very hard. Just suffice to say, T and U do not have to be the same type anymore. Okay? Now, what I want you to do is pretend like this main has one of these at a time. Okay? Just, we're going to look at one of them at a time. So pretend that this is the one. What do I get? What's the answer? That's right. Look what happens. A version of Atom with those 2 types is created. All Atom does is add them together and return the sum. So we get 7. How about if this one is the only one that we invoke? What's the return type? Double. That's right. Look, whatever is here is going to be here, right? So it's going to return a double. So this is going to be 7.2. Good. And how about in this case, the third case? It happens to truncate, okay? You get 7 because you're returning an integer. It happens to truncate. You can play with that if you like. All right, how about this one? Yeah, can you add strings to ints? No. Don't even look. Okay? That plus operator, even though you want it to concatenate it, even though you want it to be high 4, you get a compile error because plus is not defined. And of course, to fix it, you could overload it. All right, and how about this one? Same story. Okay, we don't know how to add integers and strings. And you get a compiler error. The compiler will say, I can't do that. I know you want me to do that. I can't do it. Okay, last thing of the day. Here's how compilation works up until you have templates in your toolkit. Okay? This is the .h file, this is the .cpp file, and this one is the client code. Okay? The way we compile these things is to #include the .h here and #include the .h here. And effectively, we compile this together into a .o, and we compile, by those includes, we compile this together into its own .o file. This is what your make files do. This is how it orchestrates your compilation. And then you link those together via the linker. Okay? And we love that. That's really nice, especially because it allows us to encapsulate away the implementation of the class. Okay? But the compiler, in the context of templates, needs to know what versions of the classes to build. And as such, the compiler needs to see the functions and their use all at the same time. Okay, that's one of the constraints. The other constraint is we, as programmers, never want to demand that the client change their behavior. So we still want, in main, we still want to see #include the .h file. Okay? But the question is, where does this go? What do we do with that? And the answer is, by convention in this class, there are several different conventions, but this is the one I like the best. We take the .cpp file and we include it at the end of the .h file. So here we're going to say #include the .cpp file. And then when we compile main, we're getting in order the class definition, the class implementation, and the client code. And all of those get compiled together. And the reason I don't like this is because it breaks encapsulation, right? You're exposing the implementation of your class. That's true. You just have to kind of get over it. Yeah? You guys be quiet. I can't hear him. What? I'm sorry. I can't hear you. So you have to be aware of what you need for each one of them, but this is sort of the simplest case. You can have other stuff. It would be fine.